Hey guys, welcome back to General Chemistry. Today we're going to start our series on simple gas laws. We're going to start with Boyle's Law. So the simple gas laws, just as a reminder, are where we are looking at two of the properties of gases and we're holding the other two constant, and we're going to look at the relationship between the two. Um, so the first one that we're going to look at is Boyle's Law, which investigates pressure and temperature relationship, pressure and volume relationship. That means it holds the temperature and the amount of our gas constant. All right, so Boyle's Law, let's think about a scenario that we've maybe dealt with in the past. So if we think about like a tire pump, something you can crank up and down to fill up a tire, or even a handheld one where you like fill up a basketball or something. Okay. Just some terminology to get out of the way, just because I'm going to use it. That way we're all on the same page. This thing right here that goes up and down, I'm going to call that the piston. So the thing that you pull out and push back in, we'll call that the piston. And then the area inside of here we'll call the volume of the cylinder. So the piston going up and down, and then the amount of gas that's in the cylinder here. Okay. So let's think about the upstroke going up. Okay. So this is all the way down at the bottom. We pull out on the piston. What happens to the volume inside of here? Okay, so the piston was all the way at the bottom. Now it's all the way at the top. What we're going to see is that the volume inside the container is going to increase, right? So it was down here. Now it goes up there. Volume increases. What happens to the pressure inside? Well, according to Boyle's law, the pressure inside of here is going to drop. Okay. Well, how do we know? What do we observe that tells us that's the case? Okay. So I pull up on the piston, the volume inside of my cylinder increases. And what happens to gas? Well, gas is going to go into the cylinder, right? So if we increase the volume, the pressure on the inside drops. It's lower than the pressure on the outside of the cylinder. So with the pressure being lower on the inside, gas is going to go rushing into our cylinder. Okay. Now let's think about the opposite. So piston's up at the top, and we're going to push it down to the bottom. So first thing is, what happens to the volume inside of our cylinder? Yeah, the volume decreases. Okay. And then what happens to pressure inside of there? Pressure is going to increase, right? So how do we know what's the observable change? Well, when we push down on the piston, the pressure inside the cylinder is now really, really high. Pressure outside the cylinder is low, and that gas is going to go rushing out of the cylinder into whatever it is we're trying to fill up. So into the basketball, into the tire, right? So pressure just got too much inside the cylinder, so it's going to go rushing out. So this is the concept behind Boyle's Law. So Boyle's Law is defined as the volume of a gas is inversely proportional to the pressure. The volume of gas is inversely proportional to pressure. Okay? So let's talk about this symbol here. This little fishy symbol right here is the symbol for proportional to. Okay? So it's just the way that we symbolically represent that. Okay. When we say that the volume is inversely proportional, remember the inverse of anything, so if we have x, the inverse of x is 1 over x, right? We just flip it. So when we say proportional to the inverse of pressure, that's just the symbolic representation of this statement. Okay. So what does it mean that the volume of gas is inversely proportional to pressure? Well, inversely proportional means this. One goes up, the other goes down, or if one goes down, the other goes up. So that's what inversely proportional means. So if we increase volume, we're going to decrease pressure. And if we decrease volume, we're going to increase the pressure. That's inversely proportional. Okay? So why? So remember I said I like to put the kinetic molecular theory towards the beginning of the chapter because I like to refer back to it. So here's where the kinetic molecular theory is helpful to explain what's going on. We're chemists, we want to know what the particles are doing. So as the volume in a container decreases, if we're holding the amount of our gas constant, as the volume decreases, it becomes more crowded. So more crowded means there's going to be more collisions with the side of that container. More collisions with the side of that container is going to register a higher pressure. So as it becomes more crowded, more collisions, higher pressure. The opposite is true. If we pull the sides of the container away from our sample of gas, we're going to see that there's bigger volume, so we pull the container away, and we're going to see that there's less collisions with the side of the container than there were before. It would register a lower pressure. So for all of these gas laws, we're going to look at scenario situations, okay? So we're going to look at how a scenario changes. We're going to look at some initial time. So maybe that's right here, where the diver is initially at the surface of the water, and we've got conditions that are associated with that. So we've got a pressure that's associated with him at the top. We've got a volume in his lungs that are associated with the top, so some initial condition. Then we're going to look at some final condition. So later on, what happens? So let's say this diver dives down 20 meters. That's his final destination. And then there's going to be some sort of pressure associated with that depth. There's going to be some sort of volume associated with that depth. And what we're going to do with these simple gas laws is that we're going to be able to calculate that relationship between our two variables. What was the pressure and volume initially? What was the pressure and volume at the final time? And then we can kind of solve for and math our way through this. So each one of these basic gas laws is going to have a formula associated with it. For the, I'll spare you the derivation. I won't tell you how I get to it. But for the Boyles Law, the equation is going to be like this. It's going to be P1 V1 equals P2 V2. Okay? So this P1 V1 is going to be the initial. What were the conditions when the experiment started? And the P2 V2 is going to be the final. What was it like at the end? Okay. So if we know 3 of those 4 variables, we could solve for any one of them. So let's take a look at an example. So imagine a diver was initially at 765 millimeters of mercury with a volume of 1.78 liters. What would the pressure be if the diver exhales and the volume decreases to 1.25 liters? Anytime I use a formula, I like to just take inventory of what I know, make it crystal clear what it is that I'm solving for. Okay. So imagine a diver was initially at, so that initially is going to tell me this is P1. 765 millimeters of mercury is a measurement for pressure. So while we typically use ATM, it's actually okay that we use millimeters of mercury here. Just know that our answer will be in millimeters of mercury when it spits out. So initially at 765 millimeters of mercury with a volume of 1.78 liters. Then it's going to talk about some later time. So what would the pressure be? So it sounds like we're solving for pressure. What would the pressure be if the diver exhales and the volume was decreased to 1.25 liters? So that was the volume after he exhaled. Now that we have all of our variables in place, now we just need to chug through the math of this. So plug it in and chug through it. So we've got 765 millimeters of mercury times V1, which is 1.78 liters, and that's going to be P2 times V2, which is 1.25 liters. Okay. Basic algebraic rearrangement here. So I want to get P2 by itself. I'm going to divide by 1.25 liters. Whatever I do to the right side, I also have to do to the left side. So 1.25 liters. Let's keep a close eye on our units here. So I have liters on top, liters on bottom. Those cancel. The only unit that's left in my problem is the millimeters of mercury. But that is good news because we are solving for pressure, right? That's a pressure measurement. All right, so I just need to plug this into my calculator, and it will spit out the answer for me. So we've got 765 times 1.78 divided by 1.25. And my answer is 1,089 millimeters of mercury. So another cool thing that I want to talk about here is you can pretty much check your answer for all of these problems. So we can ask ourselves, does this make sense? So what happened in this problem? Well, if we look at our initial volume and our final volume, we see that the volume decreased. According to Boyles Law, what would we expect pressure to do? Well, it's inversely proportional, so we'd expect pressure to go up. Is that what happened? Yeah, we went from 765 to 1,089. So we expected pressure to go up. It did, in fact, go up. Good possibility that that is the correct answer. So that's it for Boyles Law. Pretty straightforward, pretty easy. I hope you guys found this helpful.